Alrighty, so still in Unit 3, we're starting with heating curve or heat today with 3.3. And so last time we talked about phase diagrams and the changes between solid, liquid, and gas phases. And today we're going to kind of talk about a heating curve. Okay, so on our y-axis we have like a temperature rating, and then on our x-axis we have time. And so over time, as our temperature increases, we change from a solid to a liquid to a gas, etc. The biggest thing with this, and I don't want you to sit here and memorize all these equations because it'll drive you up a wall. And so when temperature remains constant and energy is being absorbed or released, matter is changing. Okay, so as we release energy, that's where our phases of our substances start to change. Some of us we had a little bit of an exposure to the Q equals M times specific heat times change in temperature, or triangle in temperature. And so that equation just tells us or allows us to measure the change within that phase. I don't think I'm going to go into detail about change in H vaporization or change in H fusion. That's more for upper level chemistry classes. But yeah. And so heat and temperature are different things. Just like mass and weight were different things, now heat and temperature are different things. I'm gonna blow your minds today. And so heat is just the transfer of energy between an object. So like you put your hand on a hot stove, which I hope none of you do, because that's not good. Put your hand on a hot stove. One, your nerves are gonna be, hey, hot, move it, right? But in order for your nerves to realize, or your neurons to notice that it's hot, it has to transfer energy from that hot stove to your skin cells. Okay, and so heat is just the transfer between objects of a different temperature. And we already know that like heat rises, and so hot things are always going to go up while cold things stay towards the bottom. And so when heat is transferred, we're going to use negative values. So you're going to have like a negative Q. And you might have seen that in our lab on Friday or Monday, whenever your class did it. And so when we heated up the different snack foods, did that heat transfer to the water? Think about that. So if you had a negative Q, you were correct. Some of us, we had weird numbers, or the food didn't burn properly, or cans probably weren't close enough, or we were measuring the temperature of the can and not just the water. And it's all part of human error. And so I realized that, and that's okay. It was more of an exposure to the equation than it was being accurate. And so when heat is absorbed, then we're going to have positive Q, or positive change of H. And so heat is measured in units of joules, capital J, or calories, lower c. The difference between uppercase C and lowercase c was found out in that lab. You can read the background on that. It'll tell you a little more, information. Okay, and so 1 calorie is equal to 4.184 joules. That's our conversion factor from joules to lowercase calorie. And so when we are measuring the changes between states of matter, like I said before on that heating curve, we're going to use that equation. Q equals mass times specific heat times change in temperature. Remember that triangle just means change in science. The change in temperature. So in order to find the change in temperature, you had to take final temperature minus initial in order to find that change in temperature, the change in mass. Okay. And so Q is just how much heat is absorbed or transferred. Remember, we talked about Q being negative when we're transferring heat to something, and when heat is being absorbed, it's going to be positive. Okay, so here's an example problem, and just ignore the work underneath. Excuse me. So a 25-gram sample of copper is heated from 25 degrees Celsius to 85 degrees Celsius. The specific heat of copper is 0.385 joules over grams times Celsius. Ignore the furnace behind me that's kicking in. Calculate the amount of heat absorbed by the metal. Okay. So now we just need to multiply everything together, fill in what we have for our calculation or our equation, right? So Q equals mass times specific heat times change in temperature. Remember to set up your change in temperature to be final minus initial. If you do it the other way around, you're not going to end up with the correct, you're going to end up with a negative number, not a positive number, because heat is being absorbed by the metal, right? And so that's a key in that word problem that tells you that you should have a positive Q at the end. And so we're going to take mass times our specific heat, which was given, times our change in temperature. So 85 minus 25 should give you like 60. Okay. And when you get that, it's going to end up being 577.5 joules. And so Q is a positive because it's being absorbed, 580 joules. Or if you were to convert that, remember 1 calorie is equal to 4.184 joules. And so it would end up being 140 little calories, lowercase calories. All right, here's another practice problem. And so this one, we had to rearrange, oh wait, just kidding. When heat is added during a phase change and the temperature remains constant, we're going to use a different equation. And so this is more advanced than what I'm going to have you guys do in the test, but I would like you to write it down just so you have exposure to it. If you do end up taking like a college level chemistry course, which is honestly awful, and you can ask me questions about taking chemistry in college. Not fun, for me at least. I'm not a math person. And so the change in H, or the change in heat, is equal to the mass times the change in heat fusion for that substance. And so for a melting point, that's the equation you would use. For boiling point, you want to use mass times change in heat vaporization. And so our problem down here, for example, is just calculate the energy required to boil, meaning we're going to use this equation, of 100 grams of water, and it gives you the heat vaporization. So you would just take 100 times the 540, and that would give you 5.4 times 10 to the 4th calories. And if you were to convert that into joules, it turns into a pretty high number. And so moving on to 3.4, and now we're going to talk about temperature. So temperature is just the measure of average kinetic energy of the molecules within the substance. So how fast they're moving will give you the temperature. Okay, the slower the molecules are moving, the lower the temperature. The faster that the molecules are moving, the higher the temperature. And so temperature of that object just reveals or tells you the direction of heat transfer. And so we're going to talk about the different types of temperature that we use in chemistry. And so Fahrenheit, which even in America, we don't use this. And so we aren't going to use it in chemistry either. But there are ways of calculating and converting between Fahrenheit to Celsius, Celsius to Kelvin, etc. Celsius is what we use in America consistently. Okay, it's based on pure water. That the freezing point is 0 degrees Celsius and our boiling point is 100 degrees Celsius. And then Kelvin, which is what we use in science, is called the absolute temperature scale. It's the like SI metric version of temperature. And so these units are the same size as Celsius units, but the scale starts at a different area. And so it starts at 0, meaning that it's absolute. So absolute 0 or 0 degrees Kelvin is the temperature where all motion is completely stopped. At 0 degrees Celsius, the movement of those molecules are still slowly vibrating and moving. They're not at standstill yet. And so it can't be an absolute 0 like what is used in Kelvin's unit scale, unfortunately. And so that's why we use Kelvin in science. And so this is how we're going to convert from either or. In order to go from Celsius to Kelvin, we just need to add 2.73.15 if we want to be pretty precise. Otherwise, I'm okay with you just using 273. If we want to find Celsius, we just have to subtract 273.15. Okay, so that's pretty easy, right? All right, couple of laws that I would like you to write down in your notes that kind of we come back to multiple times throughout the year. And so the mass conservation law is that matter can neither be created nor destroyed. Okay, so whatever goes into a chemical reaction must come out. Okay, and then energy conservation law. Energy can neither be destroyed or created, but energy can be transferred from one subject to another, and it will be equal no matter what. Okay, so here's a video that kind of explains the different types of energy.
Science. In this video, I'd like to talk about different forms of energy. Up first is mechanical energy. As this roller coaster moves up this hill, energy is used to overcome the force of gravity. You lose energy, but the roller coaster gains potential energy. At the top of the hill, the coaster has potential energy. As the coaster moves down the hill, it now has kinetic energy or energy of movement. So mechanical energy is the total of the potential energy plus the kinetic energy. Nuclear energy is energy stored in the nucleus of an atom. When large atoms such as uranium or plutonium are split into two smaller atoms, in a process called fission, energy is released. Nuclear power plants use this process to help create energy. Chemical energy is the energy of chemical reactions. Chemical energy of a chemical substance can be transformed to other forms of energy by a chemical reaction. A chemical reaction is one chemical substance is transformed into another. Examples of chemical energy include batteries, burning gas in a car, and fireworks. Light energy is the form of electromagnetic radiation, which means it has electric fields and magnetic fields vibrating back and forth very quickly as a wave. Visible light is the portion of this radiant energy that we can see. Examples of light energy include light bulbs, a fire, or a lamp. Sound energy is the form of energy that is associated with vibrations of matter. It is a type of wave, which means it needs an object to travel through like air or water. When you play a guitar, the strings vibrate and cause waves to travel to your ear. And finally, electrical energy is the energy that is caused by moving electric ions. Since the electric charges are moving, this is a form of kinetic energy. The faster the electric charges are moving, the more electrical energy they carry. Electrical energy powers most of the appliances and gadgets in your house. So there we go, several different types of energy. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
Right, that's it. Try some of those practice problems. If you get stuck on some of them, we'll answer some questions on Monday or Thursday whenever you return. Have a good day. Bye.